All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. We're in the middle of something last time, so let's just jump right back into it. Okay, there we go. Maybe we should actually just review what we were doing last time. Okay, so we went over the process of lagging a little bit. Went over the process of figuring out when a series absolutely converged versus conditionally converged versus diverged, and we saw that that was essentially, it's a two-step process, but we kind of did it like a three-step process because we're following our own rules and making sure that we use the test for divergence before trying anything else. And so the process was using the test for divergence to check for divergence. If that tells you it diverges, then you stop and you say it diverges. If it's inconclusive, which means you get a limit equals 0, then you move on to the next step, at which point you first check for absolute convergence. So you put absolute values around everything, get rid of all the negatives, just add up all the magnitudes, see if that converges. If that converges, then you stop. You say that the series is absolutely convergent and you're done. If that doesn't converge, then what you do is you take back the absolute values, you look at the original series, then you do another series test for that. And if that converges, then you say it conditionally converges. Otherwise, you say it diverges. And that's just a process, overall process that you'd have to go through. Someone's trying to get in here. That you'd have to go through. And it's not, like I said, each stage has this opt-out feature. So you might not even have to cover all these steps, but it's important that you know all the steps because you might have to go through all of them. So we did some examples of that where we only needed the first 2 stages to actually answer a problem here because the test for divergence was inconclusive. Here we got that the test for divergence actually works, so we could stop on the first step. And here's another situation where test for divergence worked, so we could stop at the first step. We looked at a couple different ways to look at that one. And this was one where we had to go through all 3 stages to actually come away with the final answer that a series like this conditionally converges. So we looked at that example. Then we covered, so these are all our series tests, again, summarized in one table, which tells you when to use them and what conclusions you can make. And we actually used that to come up with a general approach to series. So we now know how to approach a random series and talk about whether it converges or not. Then we looked at estimation of series. This is because actually knowing what a series adds up to can be very difficult in general. So the idea is we want to find ways of approximating series. One way to do this is to approximate them by their sequence of partial sums. And so, or a partial sum to approximate a series. And there are certain conditions under which we can check how good this approximation is. We looked in one situation, that is the situation when you're looking at an alternating series. We can actually tell very easily how good an approximation the nth partial sum is for the series. We've also noticed that we can actually determine how many terms we would use to actually get a result to a desired degree of accuracy. We also know that we can also tell if our approximation is larger than the actual value or smaller than the actual value. So you can get a lot of mileage out of that one when you have an alternating series. A couple other methods here that we skipped. Then we started talking about power series, which is, as I was mentioning, one of the most important kinds of series. So a lot of people who never really use series for anything else, they might use series in a power series context, and it's going to be very important. And today we'll actually see a little bit more about why such a thing is going to be important. So yeah, this is a new object that we started to introduce towards the end of last class. Essentially, it's just a series that looks like an infinite degree polynomial. And so that will allow us to actually do things with series that we normally do with polynomials, which are very nice functions, and a lot of things actually work out very nicely for them. We also saw that power series will always converge in some sense, and there are three ways in which they can converge. They can either converge at exactly one point, namely the point that they're centered around, or they can converge for all possible values of x, all real number values, or they will converge on some interval. And whenever they converge absolutely. So we saw the definition of interval of convergence and radius of convergence, and this is just basically talking about the interval on which you converge and how big that interval is as measured by the distance from the center that you can extend where this series will actually make sense. Then we went to the question of how do we actually find the radius of convergence and the interval of convergence? And the answer for Calc 2 is always use the ratio test. Always the ratio test. So that's never something that you're going to have to worry about in terms of how you're going to approach it, because I told you it's always going to be the ratio test for us. Not in general, but for Calc 2, every problem that I'm going to ask you is either going to involve you using the ratio test or using some fact that you know that we use the ratio test to derive. So it's always going to be going through the ratio test. And we had some examples here. I ask you guys to try for next time. So we're going to actually go through these and actually see how that was working. So that's what we were doing last time. We looked at the power series, where they converge, and what they are, where they converge. And we actually have some examples that we want to try here. So that's where we were. So now that we're all caught up, let's actually continue this story. Sure. Here was giving trouble a little bit earlier. Just want to make sure things are working. All right. So let's actually look at this guy. This is a power series. We know it's a power series because, for example, this looks like Cn x minus x naught to the n, where your Cn equals 1 for all n. Right, so it's always a coefficient of 1, and x naught equals 0. So if you plug in Cn equals 1 and x naught equals 0, you actually get something that looks like that, which if you started writing this out, you would get 1 plus x squared plus x cubed plus x to the fourth plus da da da. Right, keeps going on like that. So this is a series. It looks like an infinite polynomial, but the coefficients are always the number 1. And it is a power series by definition because it actually looks like that. So now the question is, so in other words, this was, I want to write it out. This is like 1 times x minus 0 to the n. Okay. So it's an example of a power series. Now we ask the question, for what values does this converge? So let's actually try to make it clear what we actually mean by saying this, because the first time you see a power series, it's probably kind of confusing, like wrapping your head around what it is. Okay, so you can wrap your head around kind of what it is. Okay, like I can imagine a polynomial where the degree just keeps getting higher and higher. But when someone asks you where it converges, it might be a confusing thing to actually figure out, like, what do you even mean by that question? So I just want to do a few examples that explain to you what I mean when I say, what are the x values that for which it converges? What is the interval of convergence? What is the radius of convergence? Okay, so I can ask for this question for what x values does this series converge, right? And I'm talking about power series, of course. Okay. Now, I want you to note some examples, like where this question is even coming from. If I plug in The idea is here, X is a variable, and you can actually start plugging in values for X, right? So let's say I'm going to plug in some random value so you can kind of see what I'm talking about. What if I plug in X equals 0? Right? So I go here and I plug in X equals 0 everywhere. What would happen if I plug in X equals 0? I get 1 plus 0 plus 0 squared plus 0 cubed plus 0 fourth forever, right? In other words, if X equals 0, the series equals 1. It adds up to 1, which of course, it makes sense. You know, 1 is a real number. That is something that, yeah, this power series makes sense when X equals 0. It actually adds up to 1, right? And another thing I could say, okay, what if X is equal to 1/2? What would happen in that case? Well, then the series, so I'm going to go here, and everywhere I see X, I plug in 1/2, just as if it were a regular function. So I would get 1 plus 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. So this is 1 plus 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. And I can ask, does that make sense? Well, yeah, the 1/2 plus 1/4 plus 1/8 plus 1/16. We actually already looked at that when we started talking about series, and we used that dichotomy example of, you know, splitting up a mile by dicing it into halves in forever. So we actually know that from 1/2 onward adds up to 1, and then you're adding up to 1 again. So this whole thing adds up to 2. And again, that makes sense. Right? 2 is a bona fide real number. Yeah, the series converges if X equals 2. What if I were to plug in, say, X equals 1? Right, so I go here. I would have 1 plus X squared plus X cubed plus X to the fourth, but I plug in now X equals 1. Now, what would happen if I plug in X equals 1? Well, I would get 1 plus 1 plus 1 plus 1 plus going on forever. Now, obviously, that equals infinity. That diverges. So notice this power series that I'm looking at, the sum from 0 to infinity of X to the n, it doesn't make sense for every value of X. There are obviously some X values for which it works, and there are some X values for which it does not work. So when I say something like, where does it converge? I am talking about where on the real line, what X values from the real line can I plug into the series and it will make sense. It will add up to a real number, right? Because its value will change based on what the value of X is. So when I ask, what is the radius of convergence or the interval of convergence? It turns out for these power series, there will always be some interval of X values where you're allowed to plug in any of those X values and the series will make sense. But if you plug in an X value that's not in that interval, it won't make sense. Now, it's possible for that interval to shrink as small as a single number where it only works at that specific X value. It's also possible for it to be an interval of finite length where, okay, if I plug in any X in this window, it will work. If I plug in any X outside of that window, it will not. But it's also possible for the window to go infinitely large and I'm allowed to plug in any X values. Now, clearly, this one is a situation where we are in case 2. It works for more than a single X value. And at the same time, it doesn't work for all X values. So we kind of know that there's a window of X values for which this would work. And we want to know where that window is. Obviously, going to 1 is going too far, but where does it actually stop? 3/4, 9/10, you know, like 999 over 1,000. Like, how close to 1 can I get before things start going haywire, right? I want to know what window we're allowed. Now, clearly, we're starting at 0. 0 is the center because that's the X naught. So we're opening an equal distance in both directions from 0, so around the origin. And I know that if I make it to 1, I've gone too far. But where exactly should I stop would be the question, right? What are the X values I can plug in that will make this series make sense? So when you're looking for the radius of convergence and the interval of convergence, that is the question you're trying to answer. What X values am I allowed to plug in to make this thing make sense? Okay. Now, How do you go about finding the radius of convergence and the interval of convergence? The ratio test. Always the ratio test, right? So that's something that you never have to actually, well, I don't know, right? If I ask you a question, oh, find the radius of convergence integral, like, how do I do that again? It's the ratio test. Always the ratio test. Okay, so that is what we're going to use. So the ratio test is a very specific series test, where we look at the limit as n goes to infinity of the an plus 1 divided by an, and we know it needs to be less than 1 to converge. So if I want to know where does this converge, it means I need to force that limit to be less than 1. And then I can figure out what x values will make that true. Any x values that does not make that true would not be in the interval of convergence. And so that's how we're going to proceed. Right? So for IOC, we employ the ratio test. Okay, so you would go in and you'd set up L equals the limit. Obviously, it is as n approaches infinity of an plus 1 over an. And remember, an plus an is just the entire series expression, which in this case is just x to the n. So this means I'm looking at the limit of x to the n plus 1 divided by x to the n. Okay, and so that's actually not so bad, right? All of this is going to cancel into that. And we're simply going to end up with the limit of x. Now remember, this limit is as n approaches infinity, and you won't always have to write that. I think this is something that at this point we know when we're talking about sequences, it's always as you're going off to infinity. We actually had that discussion already. It doesn't really make sense to take a limit anywhere else. So you kind of already know this part. I mean, I'll let it slide if you actually don't write this, because it's one of those things that sort of goes without saying. But generally speaking, you kind of know what the limit is. It's always going to infinity. But now, so because the limit has to deal with n, and there is no n left here, it's just the absolute value of x. This guy, x is constant in regards to n. So if I take the limit as n approaches infinity of x, well, I just get the absolute value of x, right? Because there's no n to do anything with. So the limit of a constant is just a constant. We know that. So x is constant with respect to n. So now, to get convergence, what do we need? We need L to be less than 1. So that's what we're going to do. Set absolute value of x less than 1 for convergence. Okay, and this is, of course, absolute convergence. Okay, so that actually gives you a window of x values. As long as x is less than 1 in absolute value, this series will converge. Now, by the way, we'll see another way to do this, but the fact that this number right here, let's look at this expression right here. This is equal to saying x minus 0 is less than 1, or specifically, it's x minus x naught is less than 1. But we know that that number here would be considered our r, because we had that in a table somewhere last time, right? An interval of convergence is something that can be described by that inequality, x minus the center point less than some number. That number is called the radius of convergence. So by the way, we already know that the radius of convergence is 1 here. But we'll see this another way. Because sometimes at this stage, it's slightly annoying for you to actually pick out what that r is, because you'd have to write it in this form, and not always when you get to this stage it is in that form. But if you get to this stage and you rewrite it to look like that form, x minus the center point in absolute value is less than some number, then that number is necessarily the radius of convergence. So in this situation, we already know what the radius of convergence is. It's 1. But now we have to look at the interval of convergence. Now, obviously, x less than 1 in absolute value means that x is between -1 and 1, right? So this gives us an open interval, right? It tells us all things strictly greater than -1 and strictly less than +1 will work in this series. If I plug in any value for x here, where the value of x is between those two guys, it will work and it will converge absolutely. So I can plug in x equals 0.7, x equals 0.9725, x equals 0.5, x equals 17/18, right? Any x value like that will work in this thing. It will add up to something meaningful. Now, I might not know right away exactly what that thing is, but I know that it should add up to something meaningful. It should give me a constant. And by the way, in this case, we will actually know this guy very well. We'll actually know what it adds up to specifically if we put in any x, but we'll get to that later. But yeah, this is the interval. Now, another thing that we mentioned last time, let me just remind you of that. Yeah, we mentioned last time, one or both of the endpoints may be included, which means this is not something that we know ahead of time. Generally speaking, this will be something that we have to test for. So this brings us to the ever important scenario, or the ever important thing that we always have to check the endpoints. So here we're going to check.
Quick question, didn't we already do that in the beginning? We saw that if we plug in 1, it goes to infinity.
Right, so we checked 1. We didn't check -1. But I'm going to do this again. I'm just going to do it because I want you to see like a problem fully worked out. This was what I wrote in blue here was sort of like a discussion to kind of get the idea of what I mean. But I want you to see a problem fully worked out so you can see how it would be written out. So there comes a point where you'll have the interval and you can even figure out the radius of convergence, but you actually want to know, you want to check the endpoint specifically. So that actually involves doing a series convergence test. So checking the endpoints literally means you plug in the x values at the endpoint and see what happens to the series. So check the endpoints. So the endpoints are x equals -1 and 1. So you go, okay, if x equals -1, what do I have? Well, I would have the series n goes from 0 to infinity of -1 to the n. So that would be 1 minus 1 plus 1 minus 1 plus. And now you ask the question, does that converge? And you can say, no, this diverges by test for divergence. Right, limit of -1 to the n. And this is also something that we've seen before. Like we did that way back when we were doing sequences. We actually took the limit of something like that. Yeah, that was even a little bit farther back. We actually took the limit of something like that and we saw that it was not 0 because it was jumping up and down, right? Limit of an -1 to the n does not exist, dne. Right, so the test for divergence tells us that diverges. Okay, so we know that it doesn't work at -1. So plugging in -1 is illegal, and we already know you can't plug in anything less than -1. So then you go, okay, go to the other endpoint, x equals 1, and yeah, we already looked at this, but what you would do is you would literally plug in x equals +1 into the original series formula. So this would mean it's 1 to the n and goes from 0 to infinity. Well, that's just a series of 1s, which again is 1 plus 1 plus da da da. which we know that adds up to infinity, that diverges, but you should justify it with a test. And you say this diverges by test for divergence. So to figure out, given a random power series, you want to figure out where it converges. What you're going to do is you're going to take the entire formula that's beside the sigma sign. The sigma is the summation sign. It's called a uppercase sigma. You're going to take that entire formula and you're going to put it inside the ratio test. So it's going to be, you're going to find the limit as n approaches infinity of that thing where all n's are replaced with n plus 1. And then below it, just that thing by itself. Take absolute values. You would simplify, and then you take the limit as n approaches infinity. That's going to give you some absolute value expression. You force it to be less than 1 to get absolute convergence. And then you can unfold it and isolate your x in the middle to tell you what the interval is. Then you're going to check each endpoint because we don't know ahead of time what endpoint would work from which one wouldn't. And that does involve taking the x value of the endpoint and plugging it into the formula of the original series. This will give you a series like we've had before in sections 11.1 through 11.6. You apply one of the series tests to tell whether it diverges or converges, and then you'll know I'm able to include or exclude the endpoints. So at the end of the day here, we can make some conclusions now. So this means, we know here the interval of convergence is -1 to 1, not including either endpoint. And we also know that the radius of convergence is, well, 1. And that would be the answer. Now, I mentioned that you can see the radius of convergence here, but there's another way to actually look at this. And it's going to be, well, once you actually have the interval, so you know that 0 is in the middle, and then this goes from -1 to 1. The radius of convergence, remember, is just the length of half this interval. So you know that the entire length here is 2. So the radius of convergence is just going to be that length divided by 2. Or generally, if your IOC is the interval from A, B, right? So this is like, you know, A is here, B is here, and this is where the center x naught is. Then your ROC is going to be equal to B minus A over 2. Right, so you can think of that like a general formula. Okay, so it's going to be half the length of the interval because the radius is just half of it, right? It's like the radius of a circle. Right? So you just think of the endpoints of your interval as like the endpoints of a diameter of a circle. The radius is just half that length. So you can, once you find the interval, you can find the radius easily. Though you can also find it by putting the interval in absolute values in a special form. As long as it's in this form, you can pick it out that way as well. So this is what like a full problem sort of finding the radius of convergence and interval of convergence would look like. Any questions on that? Okay. So let's move on. So here's a challenge problem before moving to the other problem. So it's not a typical question I would ask, generally speaking, because like I said, generally speaking, asking this kind of question it's very difficult to answer in general for random series. But I also did mention to you that if I were to ask such a question like this, you kind of already know where to look, right? So I'm asking you specifically, what would this series converge to? So how would you think about doing that? Like, how would you figure that out? Does anyone see a way to figure that out? Like this series, like what is it? You know? Does it remind you of anything? Or have a pattern that you can take advantage of? Do you see something or no? So yesterday we actually spoke about a general approach to series convergence. And in step 0, if asked exactly what a series converges to, then the Calc 2 student is in a very good position because there are not many kinds of series we can know what they converge to at this point. So it's either going to be geometric or telescoping. Those are only two options. So now, remember what telescoping means. When you write it out, a bunch of terms cancel each other out in the middle. So it makes the problem that much easier to get a handle on and try to set up the limit of the sequence of partial sums. But that doesn't happen here. So it must be the other one, right? This is geometric. Because notice what happens. You started off with a term of 1. And how do you get every other term? You keep multiplying by x, right? So you start with 1, you multiply by x, that gives you the second term. Multiply by x again, gives you the third term. Multiply by x again, gives you the fourth term. And you keep doing this. So it's like, it's geometric. So here, your a is 1 and your r is x. The common ratio is x. That's the thing that you're multiplying by. And we know this converges for the absolute value of r, which in this case is the absolute value of x, is less than 1, which actually coincides with what we found earlier by doing the ratio test. So that's consistent. And so we know it converges absolutely there because it's a geometric series. But we also know what the geometric series would converge to, right? So this guy, remember, it's and it goes from 0 to infinity of x to the n. It converges to what? A over 1 minus r. Now our a is 1 and our r is 1. Our r is x. Right? This is like your a over 1 minus r. So it turns out this series is actually exactly that function. And you can realize here that this actually works for the values that we tested earlier. When I plug in x equals 0, I get 1. If I plug in x equals 1/2, I would get 2, and so on and so forth. And I can immediately tell you, if you plug in any permissible x value, exactly what the answer would be, right? So you tell me, oh, what is x's of 3/4? I can plug that in here, right? And then I think you'd get 4, right? So yeah, so this series is actually this function. At least it's this function when your x is between -1 and 1, not inclusive, right? So this actually works out at that point. So one thing you could do, you can look at this picture. If you look over 1 over x, we know what that looks like. 1 over x minus 1 means a shift 1 unit to the right. And then you take the negative of that, you get 1 over 1 minus x. So this will look like, we kind of know what this picture is going to look like. So this would occur at 1. And then we'd have the right side doing this, well, the left side doing this, and the right side doing this. And essentially what we're saying is between 1 and -1, so from here to here, this part of the function is described by a power series. So over here, if this is your f of x is equal to 1 over 1 minus x, here your f of x is actually the same as writing down a power series. So within that window, that part of the function can be described as a series. So this part of the function, I can write it down as an infinite polynomial. Now, hopefully you're starting to see like how series would be useful here, because if you have a function like this guy versus a function like this guy, obviously one has certain advantages that the other one doesn't, right? Like to integrate one or differentiate one, it's easier than to integrate the other or differentiate the other, right? One has an obvious discontinuity, the other one doesn't, right? So there are a lot of things that we're starting to see where the power series is actually in some sense a nicer object to deal with. And this is kind of where we're going. Like we're going to end up in a situation where we're going to know how to think of functions in terms of power series. And that actually gives you a lot of benefits. And we're going to talk about some of them as well. In this class and next class, we're going to do some pretty cool things with that piece of knowledge. And it's kind of why series in this way, it's a super important thing in many areas of mathematics, even in applied, like people, but it's also true for theoretical mathematicians as well. So here's another example. This one's probably not so obvious, but we're going to figure it out, right? So if you look at this one already, hopefully you would realize that it's not geometric. So we're not going to be able to write down a nice answer for this one, but we're still going to find this is a power series by definition. So this here is, its n goes from 1 to infinity. Well, notice that it starts at 1, and by definition, our power series start at 0. So so here it's like we start at 0, and then the series starts. So here's like your C0 term, and then for everyone after that, your C0 is 1 over 2n, and your x minus 4 to the n. So here your Cn equals 1 over 2n for n greater than or equal to 1. C0 equals 0, and your x naught equals 4. And you would generate a power series like that. So this is like, it's 0 plus, when n equals 1, you get a half x minus 4 to the 1. When n equals 2, you get a quarter x minus 4 squared. N equals 3, you get a sixth x minus 4 cubed, and so on, right? So it's an infinite polynomial centered at 4, and it has the coefficients 0, a half, a quarter, a sixth going on. So this is a power series. And we want to find what is the radius of convergence and interval of convergence. So the question is, how do we do that? Don't know how to approach this one. It's the ratio test. Always the ratio test, right? So if I ask you to find the interval of convergence, radius of convergence, always the ratio test. So that's what we're going to do. So let's actually use the ratio test. So we're going to look at L equals the limit of. Now remember, we already looked at the shortcut for the ratio test. So the idea is you write down this expression when you replace n plus 1 for all the n's, and then you multiply by the reciprocal of the guy. So this is going to be x minus 4 to the n plus 1 over 2 times n plus 1 times the reciprocal of this guy. So it's going to be 2n over x minus 4 to the n. Okay. Now we're going to find that limit going to what? As n goes to infinity. It's always n goes to infinity. So now, just to make the calculations a little bit easier, like I said, it's not necessarily a step that you would take, but it's highly recommended. We're going to group like things together. So the 2n, of course, would go with the 2n plus 1. And these x minus 4s, I'll put the x's together and put all the guys without x's together. So now we can actually simplify. So here the 2's would cancel. Here, this whole thing is going to cancel with n of those. So this becomes the limit n over n plus 1 times x minus 4 in absolute values. And so now we're going to take the limit, right? So I can take the limit. Now, of course, the x minus 4 is a constant with regards to the limit because the limit is only focusing on n. So then the limit just comes down to taking the limit of this part. And we know by now the limit of that is going to approach 1 as n approach infinity. As n approaches infinity. So this will just become, x minus 4 in absolute values. So what you're going to do is you're going to set x minus 4 less than 1 for convergence. Okay. We know it's going to be absolute convergence. You can also see at this point, because 4 is the center point, it's where it's centered around, the radius of convergence is 1. But even if we don't see that right away, we will be able to see it at some other point, right? So we but there's going to be another point. So what we're going to do is we're going to flesh this out because we're going to have to do that anyway. So this means minus 1 is less than x minus 4, which is less than 1, which means your x is going to be between 5 and 3. Now, obviously, the distance between 5 and 3 is 2. Half that distance would be 1. So that's another way you can see the R of C is 1. Right. So on the number line, if we're here at 4, this goes down to 3, that goes up to 5. Your radius of convergence is going to be 1. And so we see that in multiple ways. You can see that. So we already know the radius of convergence, right? So what we want to do now is to get the interval of convergence. Then remember, we do not know ahead of time which endpoint will work. So we get to a point now where we're going to have to check the endpoints. So I'm going to go in, going to check the endpoints. So first, we're going to look at x equals 3. So what do I do here? I go back to the original series, this guy, and I'm going to plug in 3 for x. Now, if I plug in 3 for x, I'm going to have 3 minus 4, which is minus 1 to the n, divided by 2n. Okay. Now, what can you tell me about this series? Right, so we know 1 over 2n approaches 0 as n approaches infinity. We also know that 1 over 2n is decreasing. And we know that 1 over 2n is positive, strictly positive, for your n greater than or equal to 1. So this means it converges by alternating series test. So this power series actually works at the value 3. Like plugging x equals 3 is a bona fide thing to plug in. But then we have to deal with 5. Right? So we go to the original series, which is this guy, and I'm going to plug in 5 for x. So I plug in 5, I would get 5 minus 4, which is positive 1. So I get positive 1 to the n, and then, which is just 1, right? 1 to the n is just 1. And then, because it's 1 to an integer. And then I would just have 1 to the n, or 1 divided by 2n. So the series in this scenario would look like 1 over 2n. And you can say this diverges. Since it's harmonic, right? Because this is just like 1/2 times the harmonic series, right? You could also use the p series test, right? This is a p series with p equals 1. But it's okay to just say harmonic as, p series with p equals 1, that's called the harmonic case. So when you mention harmonic, that's like what you're saying in a very short way. So in other words, this works. It converges when x equals 3, but it diverges when x equals 5. So it works at the left endpoint, but it does not work at the right endpoint. And so now you can actually make a conclusion. The interval of convergence, well, that's just going to be from 3 to 5, including 3, but not including 5. And the radius of convergence is just 1. So that's the problem at a glance, right? So it's a very important problem type. I'm definitely going to ask you about this stuff. So are there any questions? Should clear it up now. Right. So you're given I give you a power series and I ask you, what is the radius of convergence and the interval of convergence? You always use the ratio test. So you're going to create the same limit that is required in the ratio test. You're going to do your simplification. You're going to take the limit as n approaches infinity. You're going to force that to be strictly less than 1 because that's what you need for convergence. This will allow you to open up the absolute values, get an interval going. Half the length of that interval is going to be the radius of convergence. But to get the full interval of convergence, you have to check the endpoints individually. You don't really know ahead of time what's going to work from what's not going to work. So you're going to plug in the left endpoint, plug in the right endpoint into the original series. So you'll get a series without x's in it, and you test that for convergence using, one of the methods we learned through 11.1 to 11.6. And then you can come back and say, okay, this endpoint is included or not, and that will give you the full interval. And so that at the end, you can conclude, this is the interval of convergence, this is the radius of convergence. In other words, this series will make sense as long as I plug in any value for x between 3 and 5, where 3 is allowed, but 5 is not. And so it converges on an interval with radius 1, where it converges on the left endpoint, but not on the right endpoint. So now I have this infinite series, and I can tell you exactly where it will work. It will work when x is all these specific x values, right? And the ROC is just another measure of just telling you how big the interval is. So that's how big the intervals would be. Any question on that? Okay, let's do another example, which, yeah. I think that's the last example for this thing. So say I give you this integral. And again, this is a power series. So here, this is like, n goes from 0 to infinity of 1 over n factorial times x minus 0 to the n. So this is like your Cn is 1 over n factorial, and your x naught is 0. And so that gives you a power series. So this would look like 1, and these plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus right? So it is an infinite polynomial where the coefficients are given by this sort of expression, 1 over n factorial. Okay, so it's a bona fide power series. That's not our concern at this point, though. Just knowing it's a power series is good enough for us. What we care about is what is the set of x values for which it converges? What is the interval of convergence and the radius of convergence? So how are we going to figure that out? This one looks complicated. It has a factorial in it. I don't know what to do. I'm going to panic. I'm not going to get this. No, we don't panic because it's always the ratio test. Always the ratio test. Whenever this is the question, it's always the ratio test. So you're just going in and you're going to be like, we're going to use the ratio test. Or we employ the ratio test. We use the ratio test. We do whatever to the ratio test. So we're going to look at L, which is the limit of an plus 1 times the reciprocal of an. Clean this up a bit, put the factorials together. Obviously, this is going to cancel into that. And we already know that n plus 1 factorial is just going to be n plus 1 times n factorial. So this cancels the factorial part. And so we end up with limit 1 over n plus 1 times x. So now, again, remember the limit is with respect to n, right? N is going to infinity, right? We're not moving the x. X is a constant at this stage, right? So now we're going to take the limit of the first part, but what is the limit of 1 over n plus 1? Well, that goes to 0. So this whole thing goes to 0. Now, the nice thing about 0 is it's less than 1, right? Always. 0 is always less than 1, right? 0 is a constant, 1 is a constant. They're not moving. So 0 is always less than 1. What does it mean when we end up with 0, end up with a number that's always less than 1? Well, it means it doesn't matter what x is. Like, no matter what I plug in for x, this is always going to be 0, which means any x value would work, right? So this actually means the interval of convergence is the entire real line, because this means works for any x. Right? No matter what we plug in for x, it will work.
And so would our radius be infinite?
So the radius would be infinite. So our radius of convergence is infinity. Right, which is one of the possibilities. I don't think that's actually like strange or anything. That was always one of the possibilities in our table. Right, so that's case 2. Converges for all possible x values, and I put it in another table what that actually means. Yeah, r can be 0 or r can be infinity. And when r is infinity, that just means you have all the x values can work. So yeah, so here, no matter what x is, you can, this series will work no matter what you plug in for x. It doesn't matter how small x is, how big x is. I can plug in x equals 0, this will work. X equals 1,000,000, it's still gonna work. X equals 1,000,000,000,000, still gonna work. X equals 15, it's gonna work. X equals pi, it's going to work. X equals minus 17.395, it's going to work. This will work on the entire real line. No matter what I plug in for x, when I plug it into this series and I get this infinite sum, it will add up to something, right? Something meaningful. It will add up to like a real number. And that's a very interesting thing to think about. So we're going to take a break right here, because this is actually going to be a nice segue into the next section. But yeah, so here's a situation when you have that all real line radius of convergence is infinity. Basically, all that means is when you set up the limit for the ratio test, the output is a value that is always going to be less than 1. It's going to be a constant, no x's in it, it's less than 1. So it means that no matter what you plug in for x, there's no x present to change anything. So it'll always work. So we'll take a break for now, and I will see you guys soon. All right, so let's continue. So we looked at an example that has an infinite radius of convergence, so it converges for all real numbers x. We plug into the series, it will add up to something that makes sense, not infinity or some number that we can't settle on. It will add up to a real number. That's a pretty cool example. But that's how you know when something like that happens. You get an answer that's always less than 1. And it doesn't matter what x you use, that will be the case. Now, we saw something just a couple examples earlier that we might have glossed over, but it's actually a very important idea. We could look at a function. You know, f of x was 1 over 1 minus x. And we saw that it can be represented by a series, namely the series x to the n. for x between 1 and -1. And it was very this is kind of very useful because this actually gives us a shortcut to actually compute this series, right? And this, of course, is a very nice series. It was a geometric series, so we always kind of had this option. But it makes you wonder, how many other functions out there can we use series to represent them, or are series always like, is there another identity for every series? Like, is there any power series I look at some function out there that I can use and make use of, and to actually evaluate series based on some other function that's out there? And so we want to expand on this. Right, like how far can we push this whole idea of using a function and a series in kind of as representations of the same thing? So this leads us to the next section, 11.9, where we're going to be representing functions as power series or using known power series. So there are actually a couple. Well, there are many ways to actually approach this idea where we take a power series, and we want to relate it to some function or vice versa. But in this class, we're really going to talk about two ways. So one way is very specific. It depends on some previous knowledge that you have. And another way is going to be constructive, like you'll be able to construct it from scratch, right? Like I could give you a function and I'm going to show you a way where you could develop a power series from that function. And how useful this is will depend on the function, and whether or not it can actually help us in calculations is going to be very dependent on the particular function, the particular series. And where it's useful is also dependent. So for example, this notion, the idea that I can look at the function of 1 over 1 minus x and think of it as a series, it only works in this window. It doesn't work outside that window. So even when it is useful, there are times when it's only useful in a very limiting sense. So there are a lot of things to worry about here. Like even if we could kind of do this, look at all our functions like series, there's also always the option to, there's also always the concern, not only when can this be done, but where would it work if it could be done, right? So we're actually going to look at ways for how to write some other common functions as series. So like our exponential function, our cosine function, or sine function. And by extension, we can write a bunch of other functions as series representations. But we're actually going to, in this section, explore the idea of using a known power series to develop power series for functions that we might not know right off the bat, like off the top of our head. So here's how we'd actually go about doing that. So here is an example. I don't know why I labeled that example 2. So this is actually the first example in this class, in this section. So let's say I have this function, f of x equals 3 plus x. And let's say I wanted to find a power series representation for this function. And I wanted to talk about where would this series actually make sense. On what interval would I be able to say that this function is the series that I'm using to represent it? Okay, so that's what we're going to do. Now, in this section, what we're going to do is we're going to use something that we know the series of to kind of talk about the series of some function that we don't know the series of. So it turns out that I can actually kind of algebraically manipulate this function to be something that's very convenient. Now, you kind of know, I think, what series we would actually use, because at this point, we literally only know one, right? Like we literally only know how to represent one function by a series. We didn't do any other examples. So if I'm going to use a known power series to represent anything, this is the guy I'm going to use, right? 1 over 1 minus x, I know can be written as that series. So the idea is the following. If I have a function, if I can get that function manipulated to look like the function part of a power series relationship, I would be able to alter the power series part to get a corresponding power series for this function. So in other words, I need to make this function look like 1 over 1 minus x. It's a long way of me saying that. If we can get this guy to look like 1 over 1 minus x, I would be able to find a power series for this function. So how can we do that? Well, obviously, we just try to make everything look like 1 over 1 minus x. So the 3 is an issue because we don't have 1 over 3 minus x, it's 1 over 1 minus x. So the first thing you want to do is you want to get rid of the 3. How would you get rid of the 3 without changing the value? Well, you could factor it out. So I could just go, all right, I can actually take out 1/3 and I would be left with this. Okay, so far so good. Not perfect, but we're getting there. The next thing, obviously, is that there's a plus sign here, whereas with 1 over 1 minus x, there is a minus sign there. Again, not a big deal in mathematics because I can write any positive sign as a negative sign at will by just thinking of it as the negative of a negative. So that's what I'm going to do here. Think of this as 1 minus a negative x over 3. Right? And so now this part, the right factor, actually looks like 1 over 1 minus x. I mean, if you were to sort of like let x equals minus x over 3, this looks like a third times 1 over 1 minus this symbol, right? Which we know would translate to the series of that symbol raised to the n and goes from 0 to infinity. Because it looks like 1 over 1 minus x, I can literally just, instead of x, I'm going to take this entire expression and plug in the place of x, right? So that's what I'm going to do. So this is actually 1/3 times a series of x to the n. But in this case, my x is now minus x over 3. Now this I can actually clean up a little bit. The nth power, I can distribute the nth power across the division and multiplication. So this is like minus 1 to the n, x to the n over 3 to the n. And then that 1/3 outside, I can multiply it back in because we know constants can factor in and out of series. That was a series property that we have. So this can be written as and that is a power series. Our c sub n is equal to minus 1 to the n over 3 to the n plus 1. And it's centered at 0 because it's x minus 0 raised to the n. That's where we get x to the n from. So this is a power series, right? Cn is minus 1 to the n over 3 to the n plus 1. And our x naught equals 0 in the power series form. Right? So one way you can actually do that and is just kind of this idea of just substituting. You can also notice that you can notice that 1 over 1 minus x over 3 is just the sum of a geometric series with a equals 1, r equals minus x over 3. Which, by the way, is how we can actually find out where this series would work. So if I want to find out like the radius or interval of convergence, so we can ask, where does this series work? Well, again, you could do the ratio test, but we've actually already done the ratio test for something like this, and we found that this works when x in absolute value is less than 1. But in this case, our x is, we saw earlier from the ratio test, this works if our R in absolute value, which in this case is minus x over 3, is less than 1. Now, we also saw this also from geometric series, that this would be the case. So in other words, this is the same as saying absolute value of x is less than 3. So this means the interval of convergence is going to be minus 3 to 3, not inclusive of the 3. And you can actually see that here, like if you were to plug in 3 for x, you get like minus 1 to the n over 3, and then that would just diverge by test for divergence. Plug in minus 3, you get positive 1 over 3, summing up forever, so that's going to diverge. So IOC is this, and the radius of convergence is 3. Right? And like maybe I could like write that out. So I could say check the endpoints. You know, if your x equals minus 3, what would happen to our series? It's this guy. Plug in minus 3. I would get minus 1 to the 2n x to the n times 3 to the n over 3 to the n plus 1. This, of course, is just a series of 1/3. Right, so that's just 1/3 plus 1/3 plus going on forever. Diverges by test for divergence. And if I plug in x equals 3, then this would just be, you know, minus 1 to the n, 3 to the n over 3 to the n plus 1. This is just going to be the series of minus 1 to the n over 3. And again, diverges by test for divergence. So all of this here tells me that that is the rated. All of this here tells me that is the interval of convergence. But in this case, we could kind of cheat and know that it wouldn't include the endpoints because we're literally using a geometric series to determine this. And we know that the geometric series behaves in a certain way. So yeah, so this function, 1 over 3 plus x, I can use the fact that I know what the power series for 1 over 1 minus x looks like and actually generate a power series for this guy. So I can actually write this function also as a power series. Now it doesn't work everywhere. It only works when my x is strictly between minus 3 and 3. But you know, within that window, I can think of this function as being one and the same. This means f of x equals 1 over 3 plus x can be thought of as the series from 0 to infinity of minus 1 to the n x to the n over 3 to the n plus 1 for, you know, x between minus 3 and 3. So at this point, you might be thinking, whoop-de-doo, Jhevon, fine. We can write this simple function, 1 over 3 minus x, as an infinite sum. Congratulations. You just made my life harder. But no, you're going to see that this actually makes your life a lot easier. But we're eventually going to see that. For now, let's actually just do some more examples. So here was an idea of using a known power series to develop a power series for something that is yet unknown by algebraic manipulation to kind of force something to look like a power series where you can just replace the variable part in that general power series formula and figure out a power series for something that you didn't know about. But this can actually get a lot more interesting than one might think. Like you can even get something where it's not exactly like the guy that you would know before, but you can still actually do something about it. So here's another example. Here's another function. 1/3 plus x squared, right? So now there's a very common first approach that someone might do when looking at something like this. Like, how would we actually approach this? So a common first approach, which, I mean, it's not exactly wrong, but you're not going to get anywhere fast, right? So is to think of this 1/3 plus x squared as, 1/3 plus x times 1/3 plus x. And then, I know how to write this as a series. So this is a series, and then that is a series. And then multiply out. But remember, you're multiplying out two infinite sums here, right? So to group like terms and all that stuff, it's going to be a nightmare, right? Especially if you want to generate a bunch of terms, it's just not practical to do it this way. So this is difficult to combine into one series. Okay, so there is a better way, or better in terms of more convenient, a more convenient relationship between 1/3 plus x and 1/3 plus x squared is, okay. Can anyone see a more convenient relationship here? Yeah, but that's not convenient. Like in terms of like, what is the relationship between 1/3 plus x and 1/3 plus x squared that I can exploit? That's not just, it's not just saying that, this being that squared just means I'm taking this one and multiplying it by itself. That's one relationship, right? Oh, this one is just the square of the other. I want another relationship, something that would be perhaps more convenient. Another way to describe the connection between these two. Any guesses? All right. for one, to make things a little bit more exciting, and two, because I'm not above bribery, let's actually do some of that. For 3 test points, if you can tell me a relationship between this in 6 seconds, I'll give you 3 additional points on test 1. Go. Ah, time's up. No one did it. Come on, I was giving away free points. Come on. Okay. The derivative is the relationship. Right? If you differentiate something that looks like 1 over x, what is the result? You get 1 over that thing squared, right? Of course, with a negative, but again, the negative doesn't matter. We can factor constants out, but that is a relationship, right? So notice, if I were to take the, well, I'll write it on the right side. This guy, 1 over 3 plus x squared, I can think of that as the negative derivative of this guy. So a derivative is another relationship between these two. We're in a calculus class, so, you know, when you think of relationships, limits, derivatives, that sort of thing, you would actually think about, you know, it's one of the relationships that should always be on the top of your mind, right? We're in a calculus class, of course. Right, now, does that actually help us? Well, we're going to see that it does, because here's the thing. So here we have the negative derivative of this guy, 1 over 3 plus x, but I know what that is as a series. That is this guy. So what I really have is the negative derivative of this series. Okay. And I might say, well, how does that help me? Can I actually differentiate this series? Well, yeah, because where we actually care about this series, which is on the interval from -3 to 3, it's absolutely convergent. And we know that we can actually split the derivative across a sum of an infinite sum in the case of absolute convergence. So that allows us to do this kind of trick, which is interchange the summation and the derivative sign. So the derivative of this infinite sum is going to be the sum of the derivatives. And again, we can do this. This is legal to switch the d dx and sigma because we have absolute convergence. Right? Remember that kind of convergence that I told you was super important? We're starting to see why it's important. Like, we actually can't do calculus without doing that. It would not be true that we can make this switch if we didn't have absolute convergence, because this sum could change values. And so when I distribute the derivative, that distribution can change values. And that would mean there is no real answer. The answer just depends on what order you wrote down the terms in. But because this is absolutely convergent, I can do this, like switch the integral and derivative. And so now what I want to do is I just want to differentiate this expression. Now this derivative is with respect to x, which means anything that doesn't have x to me it's a constant, right? So essentially the -1 to the n over 3 to the n plus 1 is a constant. And I'm really just leaving that constant alone and differentiating the x to the n. And so this would actually be, you know, the -1 to the n over 3 to the n plus 1. That's just a constant. But then this is becoming nx to the n minus 1 using the power rule from derivatives. Okay, so we have this guy. Now, what we can do is, because we want to write this as a power series, So the power of x, we want it to have n. And you can kind of do this thing in series where you do a shift of the index. There are a couple ways I can write this down. To make it less confusing, the first time I'm going to write it with a different letter, just so you can see that it's okay to actually do this. So here, what you can do is you can do something that's called shift the index. And it's really done via substitution, even though in practice, I don't know of anyone who would go through great lengths to write it out this way, but this is how it would go. So you would set something like k equals n minus 1 to write the power as a single variable or letter. And so this means n equals k plus 1. Everywhere you see n, you can just replace it with k plus 1. And so you would get the series minus, see this n here, I can replace it with k plus 1. This other n, I can replace it with k plus 1. This n here, I can replace it with k plus 1. And this is just x to the k. In the 3, this n would replace by k plus 1. And I can do that. So this would become the series starting at -1 to infinity of -1 to the k plus 1, k plus 1, x to the k over 3k plus 2, right? Now, the thing is, the k is just measuring the index. So this is really a dummy variable. It's kind of like saying, oh, the integral of y dy versus the integral of x dx. And you're both going from 0 to 1. They're actually exactly the same, right? The fact that your y is representing the variable instead of x means nothing, right? So they would actually give you the same value, right? This you would go y squared over 2 between 0 and 1. So the answer would be a half. This you would go x squared over 2 between 0 and 1. The answer would also be a half. So these two are exactly the same, right? So this is the same. And in a similar way, similarly, if I write down two different series that are exactly the same, except I change what variable I use to represent the index, it doesn't matter. So if I have a series, k goes from 0 to infinity of some f of k, it's exactly the same as if I just wrote n instead. Right? It's the same. Right? So right now, because I want to write things in terms of n just for aesthetic reasons, I can actually just write this as n goes from -1 to infinity, -1 to the n plus 1, n plus 1, x to the n over 3 to the n plus 2. Okay, and this is what it means by shifting the index. Notice that this is equivalent. Why we call it shifting and not substitution is because most people would do this thing. This is equivalent to shifting. Everywhere you see n, you shift it to n plus 1. So you kind of, instead of using k as a placeholder, you just go to the original, and everywhere you see n, plug in n plus 1, that would get this n to this n minus 1 would become n plus 1 minus 1 to give you the x to the n, right? So you can kind of shift all n's all over, just add 1 to all n's, and you actually get the same, you actually get an equivalent series, right? So you can move forwards or backwards like this. This is another thing you guys, I mean, if you're going to do like differential equations at some point in the future, you're talking about series solutions of differential equations. This is something you're going to do all the time, like shifting in indices. So I can take a series, take the variable that the series is moving, and I can shift it to the left or to the right at will. Just replace all these guys with them plus something or them minus something, and the series you'll get will be exactly the same. There's another thing though. This guy actually starts at n equals -1, which is weird, right? We want our power series to start from 0. So when you have something like a power series starting from somewhere where you don't want it to start, there are a couple things you can do. One is, if n is positive, which means it's bigger than 0, then it's easy. You just assume all the CNs are 0 up until you get to that point, and you're done. It's just 0 plus 0 plus 0 plus 0 plus starting from n equals 4, moving onwards. Okay. When your n is less than 0, what you want to do is you want to evaluate the expression a little bit. So you'll evaluate it at x equals all those lower values, and then you will get a constant that you can put into the C0, and that would be how you proceed. So here what we're going to do is we're just going to evaluate at, to fix this, evaluate the series at n equals -1. i.e., plug in n equals -1, see what you get. So I go to this series, I'm going to actually plug in n equals -1 everywhere. If n equals -1, I would get minus, actually just change the scale here, -1 to the 0 times -1 plus 1, x to the -1 over 3 to the 1. And notice that that is 0 because of the -1 plus 1, right? So when n equals -1, it is 0. So we can start at n equals 0 without consequence, right? Right. Starting at 0 doesn't matter, because if I went back one step to n equals -1, I'm just adding a 0, right? It's going to be 0 plus starting from n equals 0. So I can just shift back to n equals 0 and we're good here. If this was a 0, this was not 0, then I would just consider that to be a part of the C0 term. And I think we're going to see an example like that later on. So I don't think at this point we have to worry too much about it. So finally, so this means the 1 over 3 plus x squared, I can think of this as a series. And by the way, I can move this -1 inside. Ugh. I hate it that it does that. Like, who programmed that to behave that way? I don't do that because it's going to jump all the way to the top. N goes from 0 to infinity. I can take that minus from the outside here and move it inside. It's going to multiply the -1 to the n plus 1 by another -1. So it's just going to bump up the powers. It's going to be n plus 2, x to the n over 3 to the n plus 2. Oh, I'm missing an n plus 1. Right, and this works for, again, x is between -3 and 3. So I can actually figure out a power series for this guy by using differentiation. And again, we can check. it's always good practice because you never actually know. Check endpoints. You know, x equals 3. We would get the series of -1 to the n plus 2 times n plus 1 over 9. That clearly goes off to infinity. Diverges by, oh, that actually doesn't go off to infinity because it's the plus or minus 1 is actually, so I can just say diverges by test for divergence. My x equals -3, then I would go in here, plug in x equals -3. That would actually always give us a positive one. So it would be -1 to the 2n plus 2, which is always even, n plus 1 over 9. So that's just going to be the sum of n plus 1 over 9. Now that goes off to infinity, obviously. And the limit of an equals infinity. So we can say that diverges by, again, the divergence test. Because in this case, limit of an dne, in this case, limit of an equals infinity. So that's our power series, and that is the interval on which it works. And the relationship here was just, again, we want to use a known power series to develop a power series from a function that we don't know of yet. So I actually know the power series for 1 over 3 plus x, and I want to find the power series for 1 over 3 plus x squared. It turns out that a derivative relationship connects these two. And because the series, a power series, is absolutely convergent, I can do term by term differentiation. That's what this is called. And I think I put that in notes at some point, at some later point. So I won't write that down. But this idea of doing this is called term by term differentiation. Because differentiating the infinite series just means you're differentiating each term and adding it together. So it's just a sum of derivatives of terms. So it's called term by term differentiation. Any questions on this?
Maybe this is just a general question, but when you're plugging in or like testing your endpoints and you plug in x minus 3 and x plus 3, why does the function change? Like you have like -1 to the n plus 2, and then for -3, it's 2n plus 2.
Oh, I mean, because it changes based on what I plugged in. So when x equals 3 versus x equals -3, x equals 3 means I literally go here and plug in 3, right? So I would get the series of -1 to the n plus 2 times n plus 1 times 3 to the n over 3 to the n plus 2, right? Now in this case, the 3 to the n would cancel that, and I'm left with 3 squared in the denominator. So I just have the series of -1 to the n plus 2 minus 1 n plus 1 over 3 squared, which is what I have here. In the event that I plugged in a -3, this is -1 to the n plus 2, n plus 1. This is -3 to the n. But minus 3 to the n, I can distribute the n across the product. So this is minus 1 to the n plus 2, n plus 1. This is minus 1 to the n times 3 to the n. Right? Now, this and this will combine, right? The minus 1 to the n plus 2 times the minus 1 to the n. When you're multiplying things of the same base, you add the powers. So the new power just becomes n plus 2 plus n. So the new power of that is 2n plus 2. Then I have this n plus 1. Then I have this 3 to the n over 3 to the n plus 2. This would cancel into that. And so I have the series minus 1 to the 2n plus 2 n plus 1 over 3 squared.
Very helpful. Thank you.
Right. So that's what I'm doing here. So I'm literally when I check the endpoints, I'm literally plugging in that x value and then simplifying to get a series. It's just that in this case, I don't know what just happened. It's just that in this case, when I plug in my -3, it's raised to the nth power. And so I have -3 to the nth power is the same as -1 to the n times 3 to the n. And so it affected the -1 to the n portion as well. Okay, so thank you for your question. Hopefully that helped. Okay, I think this is the last example. It's not quite the last example, but it's the last thing where I'm going to show a certain trick. So yeah, so let's say we have this instead. I want to find the power series of this guy based on a known power series. And so I can ask the question here, what's the relationship between, say, ln of 3 plus x and 1 over 3 plus x, which is the guy that I know. I'm basing everything off the fact that I know that power series, right? Okay. All right, 6 seconds again for 1 point on test 1. What's the relationship?
Derivative.
I can't hear you.
Derivative.
Derivative of what?
Natural log of x, 3 plus x would be 1 over 3 plus x.
Right, so I'll give it to you, but that's kind of not where we wanted to go, because, but technically you're correct. Because I want to know, what did I have to do? Oh, don't want to erase that. What did I have to do to the 1 over 3 plus x to get the new guy that I want to figure out, right? So I want the relationship to be in that direction.
You integrate it.
So it's the integral, right? Which is kind of like the derivative. So who was that? Was that Eddie that said that?
It was me, Maxim.
Oh, want to make sure. I saw a bunch of things light up. All right, I'll give you a point. All right, so yeah. So that's going to be the relationship. So it turns out that if I were to integrate 1 over 3 plus x, that would give me the ln of, technically it's the ln of absolute value of 3 plus x, but I can, because I know my x limits, right? This is just the same, and technically this is plus c. But this is just the same as ln of regular parentheses 3 plus x plus c for x in this interval, right? Because then your 3 plus x will always be positive in that range. So I can kind of ignore the parentheses. By the way, this was actually a common error that showed up in test 1. There were a bunch of places where people were integrating like 1 over x and they should have gotten the absolute value, and they didn't put the absolute value. And there was even a problem where a lot of people said that the answer was incorrect because I have to log a negative thing, so this diverge, but the truth was no, because it should have been absolute values. So having a negative inside wouldn't have mattered. So that was, be careful of that. Remember the integral for this, the absolute value signs are actually important, right? You remove them when you know for a fact you can remove them because you have some other outside information which guarantees that what's inside the absolute values is 0 or bigger. And in the case of ln, it has to be strictly bigger, right? You can't have ln of 0 either. So you have to, we know this is positive based on the x values that we know. We know the power series for this only works with these x values, and with those x values, this is the 3 plus x is actually a positive, a strictly positive number. So we can actually just think of the ln without absolute values as being that. So yeah, we're going to do that. So now we can actually make this idea. So ln of 3 plus x, I know is actually the antiderivative of 1 over 3 plus x dx. And then, so the whole point is to write a power series to represent this ln function. So what I'm going to do is I'm going to take advantage of the fact that I know the power series for the 1 over 3 plus x function, which that's going to be the series, and that was minus 1 to the n x to the n over 3n plus 1. That was it, right? Yes. So we have that. And now, how do you actually integrate that? Well, you integrate term by term. So I can switch this. I can move this. I can switch the series and the integral. Why can I do that? Because I have absolute convergence, right? So this means here, since we have absolute convergence. Otherwise, this step that I just took was illegal. But that I'm allowed to switch the series and the integral because of absolute convergence. And I already mentioned that this is equivalent to ln of absolute value of 3 plus x. If you know your x is in minus 3 to 3. So in that window, we have absolute convergence. This means I can take the derivative of each term of the integral. So I can integrate each term and then take the sum of that. And of course, the integral is with respect to x. You see the dx there. So this means that the minus 1 to the n over 3 to the n plus 1 part is just a constant, and I'm integrating x to the n, which is just, it's a power rule. So this would be minus 1 to the n over 3 to the n plus 1. Then it's x to the n plus 1 over n plus 1. Now, plus c. Don't forget the plus c. Okay. Put a meme on the last test about always writing plus c for a definite integral. It applies even in the case of infinite series, right? So your plus c, you can actually think of this as a series of constants, you know, a series of constants that make up one big constant. So, but you don't need to know, you don't want to think of this as kn. I want you to think of it as, you know, like k sub n, or the k sub n constants. You don't have to really think about it that way right here, but technically speaking, that's what it would be. When you integrate each term gets a constant. So you integrate the first term, you get a constant, integrate the second term, you get a constant, integrate the third term, you get a constant. You can group all these constants in a separate series, and they're going to be a big plus c, but it's really like a sum of all these infinite number of constants, right? But there's still going to be a plus c. And so Yeah, so that's going to be that. So now here, again, we have our n to an n plus 1. We actually don't like that. We want to be x to the n to get our form. So what we're going to do is we're going to shift. Every n, I'm going to shift to n minus 1. So the n plus 1 power will become n minus 1 plus 1. And so it just becomes n. So everywhere I see n, I'm going to shift n minus 1. So this would become n equals 1. I'll highlight that because students tend to miss that. But everywhere I see n, I'm going to replace it with n minus 1. And I would get this series. So this means that my ln of 3 plus x is actually equal to the series n equals 1 to infinity of minus 1 to the n minus 1 x to the n over n times 3 to the n plus some constant. Okay. Now we're not done because we need to know what the plus c is. And so what we can do here is we can actually plug in a very convenient value for x to find the c. And of course, that x value that we plug in has to be within the interval, right? It has to be between minus 3 and 3. So the idea is, can I plug in an x value between minus 3 and 3? That would be very convenient. The answer is yes. I can plug in x equals 0, for example, because that will kill the series part and leave the c part. So to find c, plug in a convenient x value. Now, convenient in this case would be something that gets me an easy calculation. So if I plug in x equals 0, the left side would just become ln of 3. The right side would just become the series of 0 plus this constant. Now, obviously, that's just 0 because I'm just adding up 0 forever. And so I would get that my constant is ln of 3. And so ln of 3 plus x as a power series is going to be ln of 3 plus this series that we got here, minus 1 to the n minus 1 x to the n over n times 3 to the n. And you might be wondering, what is that ln of 3 sticking out there? You'll notice that our series starts at 1. So the ln of 3 is actually the C0 term, right? This is, when n equals 0. So when n equals 0, we know the output is going to be ln of 3. From 1 onwards, it's given by this series. So this is actually a power series representation, right? So now we're going to be good little boys and girls. We're going to check our endpoints. Plug in x equals 3. So what I would get here is ln of 3 plus the series, n goes from 1 to infinity of minus 1 to the n minus 1 over n. This converges. Ooh, we converge at an endpoint here. It converges by the alternating series test. Minus 1 to the n minus 1 over n is an alternating series. The an part is 1 over n. This is positive, it's decreasing, and the limit approaches 0. Therefore, the alternating series test tells us that converges. So it actually works at 3. If I plug in minus 3, I would get ln of 3 plus the series This will be -1 to the. So if I plug in -3 to the n, again, I'm going to get that -1 to the n. So this will be actually 2n minus 1 over n. Now it turns out that -1 raised to an odd power is always going to be -1. So this is always going to be minus the series of 1 over n. And we know that this diverges since harmonic. So we know then that ln of 3 plus x is actually equal to ln of 3 plus the series, and goes from 1 to infinity, of -1 to the n minus 1 x to the n over n times 3 to the n for all x values someone got kicked out. Let me let them back in here. And it works for all x values, not including -3, but it actually works at 3. Which should actually make sense to you here. This is an ln. If we were to plug in -3, it gives us something nonsensical. However, plugging x equals 3, you have a feeling that it should work because it's ln of 6. So it kind of, it kind of makes sense to exist at that point. So yeah, so I put in comments here in red something that I already mentioned verbally, about the reason I can switch the integral sign and or the derivative sign with a series is because we have absolute convergence, and this is called term by term integration or term by term differentiation. So if you see that phrase anywhere in your textbook or anywhere else, this is what they mean. They mean that we're switching a series with the operation that we want to do, and so we can do this operation term by term. So before we go, I just want to show you something really cool, before we take our second 5-minute break. At least I think it's really cool. And technically it is something that I told you guys before, but now we're actually going to see it work. So hold on. So just to be clear, this is the answer for our second example. So ln of 3 plus x can be represented by a series in that way. Okay, so we're actually going to use this to figure something out. So in the example, let's plug in x equals 3. We know that we can do this because it does converge at 3. And let's actually see what we get. So we get, ln of 3 plus 3 equals ln of 3 plus the series n goes from 1 to infinity of -1 to the n minus 1 x to the not x, I'm plugging in 3 for x, times 3 to the n over n times 3 to the n. These would obviously cancel. So this means I get ln of 6 here is equal to ln of 3. I can factor out like a -1 here, and that would be minus. So that would be true. I can also then subtract an ln of 3 from both sides. This gives me minus Now, ln of 6 minus ln of 3, we know that logs, when you subtract logs, you can just divide it like that. And so this would mean that on this side you have ln of 2, because 6 over 3. I can also multiply that by a negative sign. And so on this side, I would have the series n goes from 1 to infinity of minus 1 to the n over n. Well, look at that. Remember how I told you that the alternating harmonic adds up to ln of 2? And at first it seemed like, what? Why would that add up to ln of 2? Guess what? We just saw how we know that it adds up to that. So yeah, it's very interesting. So we now know, i.e., on I'm expanding the right side now. So this is going to be, if I plug in n equals 1, get minus 1, n equals 2 plus a half minus a third plus a fourth minus a fifth plus a sixth minus da da da. If I do that pattern forever and you ask, well, what does that add up to? Does that add up to anything? I know it converges by the alternating series test, but what does it converge to? And it turns out it converges to a very surprising minus ln2. The thing is actually freezing up on me. Yeah, so we've actually seen how we can actually talk about something that kind of seems very strange. And this is not the only way to actually derive this fact, but it's one of the most accessible ways for a Calc 2 student. And it's a very surprising fact, like why would that work? But we know it works. So I think we'll wrap up there, and we will take our break now. So we'll take a quick 5-minute break, and I'll see you guys in a bit. I wasn't recording, but I guess I just said something, I repeated it anyway. How adding and subtracting a bunch of fractions can end up in something that's not a fraction. So infinite sums can be a little bit weird. So, but they do make sense in some mathematical sense, but they're not very predictable, right? You can add a bunch of rational things and get something that's irrational, which is surprising, but this is what it has to be. We know that this function is that power series. And so that's what it adds up to. Yeah, that was very interesting. So that's one cool thing that we could see from here, like these infinite sums adding up to something. But that might be like, that might feel like a party trick to you guys. So it's like, okay, wow, you showed me that this infinite sum adds up to a log. Whoop-de-doo. Okay, so here's something slightly more practical, still very mathy, but slightly more practical. I want to show you something else cool that we can do with this idea of power series. So let's actually look at this integral. So, the integral from 0 to 1 of x over x to the 9th. Okay, so the first thing I would say is that technically we can do this integral based on what I've told you, because this is something that technically partial fractions could work on, because the denominator is the sum of cubes. I mean, you could go like, this is like 1 plus x cubed. And so you could do sum of cubes. So this would just be 1 plus this times this squared minus this plus 1. And then you can actually do this breakdown even further. 1 plus x times x squared minus x plus 1 times x to the 6 minus x cubed plus 1. And of course, you're seeing this and you're probably just like me groaning at the fact that you would have to do this. And yeah, like, so a partial fractions there would obviously be crazy. So you'll have a constant above the x plus 1. You'll have a linear term above the x squared minus 1, which is obviously going to get some sort of arctangent in there when we do it. And then you have the x to the 6th. So you're going to have a generic 5th degree polynomial above that. So finding the constants is going to be a nightmare. And then after that, you have to do a bunch of integration techniques, jump through a bunch of hoops. Technically, we could do this though, but you wouldn't want to. And you know, if I put this problem in an exam, like that would literally have to be the only problem, and you would still hate me for it. I decided to use Symbolab to try to figure out what this is, and Symbolab, boom, cannot solve. So I don't know if this can do it at this point, but at the time where I typed this in to check it, Symbolab was like, you're on your own with this dude. Like, we don't have an algorithm to actually work that guy out. So I could describe how to do it by hand, but for whatever reason, Symbolab doesn't actually know how to do it. So I'm like, okay, let me try Wolfram Alpha. And so that is what the answer would look like. And you'll actually know here, Wolfram Alpha went in and just be like, man, I'm going to even use complex values here. It's a complex valued logarithm is a part of the answer. So whatever its thing did, I wouldn't want to do by hand either. So this is a really messy integral. And then technically we're not done. We're going to have to apply the fundamental theorem of calculus, plug in x equals 1 everywhere, calculate what that is, plug in x equals 0 everywhere, calculate what that is. It's not going to be a fun time. So yeah. So this is, you wouldn't want to do that. But okay, so I'm like, all right, so at least Wolfram Alpha can give me like an answer, an expression. So let's actually compute the definite integral. So I went on and I plugged in 0 to 1, and Wolfram Alpha, okay, gave me a nice picture, told me the answer. Do this integral, you will get 0.439285, right? And I'm sure that's like an approximation. I'm sure this like continues, but they only gave me the first 6 decimal places. Okay, so that's awesome, right? So here's the thing. What if I actually care about, I don't care about this, right? I care about the definite integral. Like for whatever reason, I need to find this integral from 0 to 1. I don't care about the formula that you give me. I just care about getting to that answer of 0.439285, right? It turns out we can actually use a series to help us do this. And we are going to use kind of the trick that I was doing before the break to actually figure this out. So let's actually figure something out that Symbolab couldn't. We needed Mathematica or Wolfram Alpha to figure it out, but we're going to do it. Look, Ma, no hands. We're actually going to do an approximation for this. And I'm going to talk about, you know, well, we're going to find the exact answer, but it's going to be in terms of a series. But then I'm going to approximate that series and show you that we can actually get close to this answer of 0.439285. And I would assume that Wolfram Alpha actually did something similar to what we're doing, as opposed to actually computing this and then applying the fundamental theorem of calculus. It would actually be quicker for Wolfram Alpha to do what we're going to do, how we're going to approach this problem by hand. So let's actually see that in action. Okay, so let's actually figure this out, which even the computer was like, man, this is crazy. What are you telling me to do here? We're going to do it by hand. So we have the integral from 0 to 1. Okay, so here's what we're going to do. I'm going to write this as x times 1 plus 1 over 1 plus x to the 9th. You might say, why would I do that? That's because in my mind, I know that there's a series that I can get the second part to look like 1 minus a minus x to the 9th. So that looks like a 1 over 1 minus x, right? So then I know a series for that. There's an app for that. Okay, so we have, this would actually be a series n goes from 0 to infinity, of the r to the n. So this is the series from 0 to 1 of x times the series minus 1 to the n, x to the 9n. Right, so this is all like inside this integral here. Now I just applied a geometric series to figure that out. I know it's absolutely convergent where once we're in the right place, which means I need my x to the 9th in absolute values to be strictly less than 1. So it turns out that this is absolutely convergent on that interval, which it will work on 0, 1. In fact, I'm going to switch this now. Let me rewrite it a little bit first. Take that x on the outside, bring it inside the series, because the variable for the series is n, so x is like a constant. This is like minus 1 to the n, x to the 9n plus 1. Now I can switch this. And I can do that because of absolute convergence. And so now I would get a series of the answer. This is just something I can do by the power rule, right? So this is going to be minus 1 to the n, x to the 9n plus 2 divided by 9n plus 2. And that is the answer. Right? So this is actually, if I were to write out a few terms, if I plug in n equals 0, I would get a half. If I plug in n equals 1, I would get, oh, I didn't actually apply the, well, that's not the full answer yet. I still have to do the fundamental theorem of calculus. We didn't do the 0 to 1. So obviously plugging in x equals 0 will kill everything. So x equals 1 is the first guy. And so the series, because I don't want x's in my answer, I actually want the actual answer. That's just going to be it. So that is the answer. I can write out a few terms so you can sort of see. So when I plug in n equals 0, yes, I get a half. Minus when I plug in n equals 1, I would get 9 plus 2. So that's minus 1 over 11. Plus when n equals 2, 2 9s 18 plus 2, I get 1 over 20. And so on. So it's an infinite series. But that is the answer. However, remember, we have something that can talk about it. This is an alternating series. Right, because it has that minus 1 to the end. You get plus 1 minus plus 1 minus plus 1 minus plus 1 times all the term. So we can approximate this to any desired accuracy that we want. Right? So if I wanted to get this accurate just as Wolfram, to get it to be 6 decimal places of the answer, I could just set a n plus 1 formula less than or equal to 0.5 zeros and then a 1, solve for n that would be required to do that. And you could actually do that. So I actually wrote that out because I don't want to like write it by hand. Right. So If I have a tolerance of k, all I have to just do is go to this formula 1/9n plus 2 and set it less than or equal to k after I plug in, replace n with n plus 1, and I can solve for n to do that. Now, what would be required to get 6 decimal places of the answer like Wolfram? Well, if I solve this for this, the 6 decimal places to get the answer, it turns out my n would need to be this, right? So I need to add up 111,000 terms, right? Which, yeah, to a human, that's still horrible. But to a computer, that's actually nothing. And I'm pretty sure when Wolfram Alpha was actually finding the answer and it realizes that, oh, you don't want the formula, you just want the values. What it did was convert this to a series and added up 111,000 things and got the answer to 6 decimal places. And if you ask Wolfram Alpha, oh, I want 15 decimal places instead, it'll just add a bunch more terms to get it to that many desired accuracy. However, notice here that in one term, maybe I'll move this over here. Notice that one term, if I stop here, the approximation will be 0.5. If I only added 2 terms, I wrote it in here, the approximation would be 0.409. Now the actual answer is 0.439 blah, blah, blah. So I could actually get accurate up to 1 decimal place by hand by just adding 2 fractions to something that, you know, Symbol Lab had a problem with, right? So that's pretty good. With just adding 2 fractions, I could get to 1 decimal place accuracy, right? Sure, you have to work a lot harder to get like 5 more decimal place accuracy, but for a computer, that's nothing. But you can kind of see the power of this method, right? Where we don't need to go through a formula, because the thing we're integrating can be very, very messy, or depending on what source we're using to do the computation, it might actually be impossible for that thing, right? Using whatever algorithm you're using to compute your integrals, it could actually be impossible with a particular algorithm. And even with an algorithm that's more powerful, that can actually get you an answer, it's like, come on, dude, you expect me to actually work with this? Can't work under these conditions. However, going through a series way, a lowly human by hand could get to a 1 decimal place accurate answer by adding 2 fractions. And obviously a computer can add 1,000,000 terms in a very short amount of time. You know, within a second can add up 1,000,000 terms and get this accurate to a certain number of decimal places. So if you actually if you actually told your computer, every time you're doing a definite integral, convert it to a power series and then try to do it, then your computer is not going to have a trouble approximating an answer to any desired accuracy that you want. Of course, providing certain conditions, you know how to find the power series of the thing you're looking at. And 2, if it's an alternating series, then we know we can approximate it in this way. But we also know that there are other approximation methods. We've only just covered one in class. But this falls under the purview of the one we covered in class. So if I were to ask you, oh, how many sums of the term do we need to get 1 decimal place accuracy? You would just set up this equation and you'd realize, oh, I just need n equals 2, and we're good. So that's actually pretty cool. So I thought that was an interesting application. So it's not just, oh, I know that this sum of fractions adds up to ln of 2, whoop-de-doo. Like, how am I going to use that in my life? Well, we use definite integrals in real life all the time. And as you can see, series can take a messy or impossible problem and actually turn it into one that's actually pretty trivial for a computer to solve, or even for a human to solve in this particular case. So this is just giving you just one idea. And in fact, when you use your calculator to calculate something, a lot of the times, the algorithm in the background is actually computing it in terms of series. back when you didn't even know what a series was, right? When you go to your calculator and plug in, what is the sine of 47 degrees? Like, how did your calculator figure that out? It used a series, right? We're actually going to see how to write sine as a series and actually evaluate that. And you're going to realize that it's an alternating series. And your computer just always knows, oh, I need this many terms to fill up this many digits on my screen. Sine is an alternating series. I'm just going to write it as a series, plug in 47, and calculate a certain number of terms to get this many decimal place accuracy. So the series is all over the place in places that you probably never realized they were until now, like I'm telling you. So there are a lot of things that you've done on your calculator where in the background, you're using series. There are a lot of things that you do on your calculator where in the background, they're using matrices, but that's an argument that I'd say in a linear algebra class. But here, like a series, when you're doing calculus, series is actually used pretty often. And there are standard series for a lot of our standard functions that you can actually program into a calculator, and that's how it would do its calculations. And you tell the calculator how to approximate to 10 decimal places or whatever decimal place would fill the screen of the calculator. But the actual heavy lifting in the background that you don't see as a human being is your calculator's adding up terms of a series. Even though to you, you're putting in some nice formula, sine of x, plug in 47, like your calculator reinterprets that as a series and adds up a certain number of terms to get 10 decimal places on the screen. And it doesn't have to add up a lot of terms to actually do that. So that's a pretty cool application, I would say. So a lot of times. Now, you might say, oh, but Jhevon, what if we have, I'm speaking for the proverbial student here. What if we have a function that we don't know how to connect the known series to? I mean, we were lucky here because you had like this 1 over 1 plus x to the 9th, which I could rewrite it. Or in the case of the ln, I could think of this as an integral relationship. Or in the case of 1 over 3 plus x all squared, I could think of this as a derivative relationship. So I could connect things to series that I know about by using integration or differentiation or some sort of algebraic manipulation. But what if I were to ask you something like this guy, right? Like what if I were to ask you about this, right? Something we actually know is impossible to integrate, like you can't write it down as a simple antiderivative, e to the minus x squared. I want to give you that, right? Which means you writing down an antiderivative for this and applying the fundamental theorem of calculus, impossible, right? Like you can't do it, right? Or what if it's sine of x cubed? Like how would you connect these guys to 1 over 1 minus x? Right? What relationship gets you from 1 over 1 minus x to e to the minus x squared? There is none that directly connects those two, in case you're wondering. So I'm glad you asked that, proverbial student, because that leads into the next section. So this idea, as you can see, we only know about one power series, 1 over 1 minus x is actually the sum of x to the n. And just by knowing that, we can do a bunch of stuff. Even things that a calculator has trouble doing, we can figure it out just by knowing that one series. What could we do if we knew many series, right? So the possibilities are, many. So we're now going to talk about that. Like, how would I actually generate a power series for something where me knowing some other known power series doesn't actually help me directly with finding a power series for this new thing, right? So that leads us into this topic called Taylor series, right? So there are two main ways to actually talk about series, generating power series for a random function. And one way, as you've seen, is to just algebraically manipulate that function or use a derivative, a calculus relationship to rewrite that function in terms of something that we actually know already, and then applying what we know as a power series there. But what if you're not in that case? So you can compute what's called a Taylor series for a function. And this is basically just a generalized method for how to generate a power series for a random function. Now, there are some caveats, there are some limitations to this method, but it's actually far reaching. And in Calc 2, you're never going to have a limitation to this method, but in real life, you can have a few limitations that you might have to worry about. But for us, this is going to be a general method for developing a power series. Even if you don't know a power series that looks like the thing that you're looking at, you can actually make one up. So let's actually get into that, right? So we want to say, we have a function f of x. We want to know, can I write it as a power series? Can I write f of x to look like something like this, right? That is the question. Now, there is a common technique or approach in mathematics where it's like, you know, you ask for forgiveness, not permission. So you kind of say, well, I don't know that I can do this, but let's just pretend I could and do it anyway. And then you try to go back to see, could I reverse engineer to get there, right? So that's an approach in mathematics, right? So you want to see, can I do something? So what you do is you just do it. And then you come back and see, did I break math to get this done? You kind of reverse engineer it and just make sure that each step that you're reverse engineering doesn't actually create a contradiction or mess up the math. And then by reverse engineering the process to get back to where you started, now you can see, oh, now I know how to move forward to get to that. And then you can actually prove that all the steps work. So that's essentially the idea that we're going to do. So we just pretend that if you give me a random function, I can write it as a power series. And we're going to use the consequences of being able to do that to figure out how would we get that power series, right? Assuming that we could get a power series, what would we have to do to make it happen, right? Like, what are the steps that we would have to go through to do that? So yeah, that's what we're going to do. Suppose we could do this. All right, what would we need to do? Well, the only thing that's unknown in a power series really is going to be the coefficients, because this part is always the same. It's really the CNs that are the thing that we don't know, right? How would I generate these coefficients? It's always going to be x minus x naught to the n, but the coefficients are going to be different, right? So that's essentially the problem. Like, how are we going to figure out what the coefficients would have to be in order to do that? Right, so observe grasshoppers, right? So let's say our f of x, so we're going to assume our f of x can be written in this form. It can be written as a power series. So it's c naught plus c1 x minus x naught plus c2 x minus x naught squared plus c3 x minus x naught cubed plus c4 x minus x naught to the fourth plus, let's stop at 4, because 4 is enough for you to see a pattern that I'm going to want to point out to you. Okay, now here's what we're going to do. We're actually going to plug in the center point. Remember, we saw this idea of evaluating a series by plugging in a certain value, and that's how we solve for the plus c in our ln example earlier. So I'm going to do the same thing. If I were to plug in x naught, then all these terms here would go to 0, right? And so I would only end up with c0. So it turns out if I have a function and I can write it as a power series, the first constant, the c0 constant, I can find that by actually just plugging in the center point into the function itself. Convenient. Okay, so how do we find the other ones? What about c1, c2, c3? So here's the cleverness of it. We're in a calculus class, so we're going to use calculus. What would happen if I were to differentiate my function? Well, the c0 constant would disappear. Then I would just have c1 times the derivative of x minus x naught, which is just 1. Then I would have 2c2 times the derivative of x minus x naught, chain rule, multiplied by a derivative inside, which is 1. Then I would have 3c3 x minus x naught squared, 4c4 x minus x naught cubed, going on. Now again, I have a lot of terms with x minus x naught into it. So what I would do is I would evaluate f prime at x naught. All these terms would go to 0. And I would just be left with C1. So it turns out the C1 constant is the derivative evaluated at the center point. Well, let's actually keep going. Is everything just going to be a derivative evaluated at a point? Well, let's find a few more so that we know a pattern. So what if I take the second derivative? The C1 would disappear. This would give me 2C2 plus 3 times 2 times C3 x minus x naught plus 4 times 3 C4 x minus x naught squared plus da da da. Now, if I do the same trick, plug in x naught, all these terms will go to 0. And so I would actually be left with 2C2. Oh, so this isn't exactly the thing. So it turns out that in this case, our C2 is actually going to be the second derivative evaluated at x naught divided by 2. Okay, so that's kind of, we're already seeing something messing up the pattern. Let's go to the third one to see if we can figure something out. Third derivative. So the 2C2 would disappear. I would just have 3 times 2 times the derivative of x minus x naught is 1 times C3 plus 4 times 3 times 2 C4 x minus x naught. Notice that the next one would be 5 times 4 times 3 C5 x minus x naught squared plus da da da. Now if I plug in x naught here, this would just give me 3 times 2 times 1 C3. So if I were to solve for the third constant, this would be f triple prime of x naught divided by 3 times 2 times 1. Now you're like, why didn't you just write 6, Jhevon? Well, when you want to find a pattern to something, it actually is beneficial to not simplify every step right away, because you want the actual numbers without simplification might hint to you a pattern. And some of you might actually already see the pattern here. What if I went to the fourth derivative? The 3 times 2 times 1 times C3 would disappear. Then I would get 4 times 3 times 2 times 1 C4 plus 5 times 4 times 3 times 2 C5 x minus x naught. Notice that the next one didn't write it out, but it would be 6 times 5 times 4 times 3 C6 x minus x naught squared.
Should the term
So
be
if I
x
plug in,
and not x naught?
if I, oh, this is not x naught, this is just x. Find the general derivative here. Now when I evaluated x naught, I would get 4 times 3 times 2 times 1 C4. In other words, the fourth constant would be the fourth derivative evaluated at x naught over 4 times 3 times 2 times 1. Right? So I don't know if you're seeing a pattern, but let's actually get to the pattern here. Dun, dun, dun. Could you actually tell me in general, what would the C sub n constant look like? Or could you actually tell me that? Let's do this. 2 points, 10 seconds. Go.
The nth derivative of x naught over n factorial.
Okay, yeah, you got it. Damn it. Okay. All right. So I owe you 3 points total now. All right. Come on, you guys are gonna let Maxim get all the free points. Come on. I'm gonna bribe people. You want me always to bribe the same guy? Answer. But yes, that is correct. This is the nth derivative evaluated at x naught divided by n factorial. Notice that this is actually the fourth derivative evaluated at x naught over 4 factorial. And that's why I didn't simplify the constants right away, because now you can see 3 times 2 times 1. Well, that's just 3 factorial. And this is the third derivative evaluated at x naught. 2 is actually 2 factorial. 2 is 2 times 1. So this is actually the same as 2 factorial in the denominator. This is the second derivative evaluated at x naught. By the way, the original function, this one is the first derivative evaluated at x naught over 1 factorial, which is just 1. 0, remember the original function is like you've taken 0 derivatives. So this is the 0th derivative evaluated x naught over 0 factorial. 0 factorial we know is 1. That was by definition. So we're just dividing by 1. So there's a pattern here. So assuming that we could write our function this way, this is what our coefficients would actually look like. So we'd actually guess that this would be the case. So we'd guess our f of x, if I wanted to write that as a power series, what would that look like? Series n goes from 0 to infinity of f to the n derivative over n factorial times x minus x naught to the n. That would be our guess for what a power series would look like. Now, I should have a cautionary tale here. Warning. The equality here does not always hold. So remember I mentioned to you, so things can break when you do this whole Maverick thing and just do it anyway and just like try to figure out the math backwards. Sometimes you do run into issues, right? But if an educated guess would be, this would be how we can generate the power series. It will turn out that this doesn't always work, in the sense that there are times when we do this kind of generation of a power series, but it doesn't exactly describe the function. But that doesn't actually make it useless. It turns out that there are cases where it does, right? So it's like, it's not like it's a useless thing that we figured this out. We just need to know that it's possible for the right side to exist and it doesn't equal to the function. It's also possible for the right side not to exist. And this is when you're trying to reverse engineer, you have to figure out all the kinks, that what could stop me from taking these steps. One thing you should actually notice is that I took a bunch of derivatives to get this to work. So obviously, this can only work if your function is differentiable in the first place. So obviously, if you're at a place where the derivative does not exist at the center point, you're in trouble. So if you were to ask me, generate a power series for the absolute value of x centered at x equals 0, I couldn't do it because I can't actually find a derivative at x equals 0 for the absolute value function, right? So that's a restriction. So it tells you that this equality doesn't always work out. There are times when I can't actually get it done. Turns out though, there are a lot of times where we can get it done. That's in another section though, where we're going to discover that. But for now, there are some things that are immediately obvious, quote unquote obvious. For one, the ability to actually do this comes with some caveats. You must be infinitely differentiable is one thing, right? Notice that I'm taking the nth derivative. N is going off to infinity. So I can only do this sort of trick if I have a function where I can just keep differentiating it forever, right? So that's one thing. Another thing is that the nth derivative evaluated at that point can't get too big. What would be too big? Too big would be something like if I plug this into the ratio test and I get a divergent limit, right? That's too big. Now, we're going to talk about exactly when such a thing would occur. And we're also going to talk about what we need to make sure that this actually holds, because we actually do know that. It's just, we learned this in a future section, right? So it turns out this doesn't always work, but there are times when it does work, and we actually know the criteria to get it to work. And it turns out it works in many cases. And so it works in a lot of cases that we want to do. So knowing this is actually very important. So that leads us to this definition. You should know what a Taylor series is, right? Now, it turns out that there's a special case here. You can actually plug in x naught equals 0 into that original function, and you get something that looks like this. And it is a Taylor series. It's just that you're imagining the center point to be 0 specifically. Such a series is called a Maclaurin series, right? But it's just a Taylor series evaluated at 0. But yeah, this is the Taylor series for a function. Suppose f is a function with derivatives of all orders in an interval, then on that interval, you can generate a Taylor series for this function. Now, notice that I didn't put fx equals this, because you cannot say that in general. I'm just saying we can create such a series of this form. Now, whether or not it equals the original function is something to be determined later. And so I did mention that here. Notice I did not say f is equal to that, because it's not true in general. It's true in many cases, but not true in general. However, it is true in this case. We can actually do this for the exponential function, and it will work. And it will actually, the power series will describe the exponential function exactly. But we're out of time, so stay tuned for the next exciting episode. But try this for next time. It is something that you need to know how to do. You're going to be tested on it, so you might as well try it to see if you know how to do it. But yeah, you're going to use this formula to generate a power series for the e to the x function. And we'll actually pick up with at that point tomorrow. So with that being said, that's all for today. Did some cool things with series, found some cool applications. And we know how to generate power series for things, even if we from scratch, right? Once we can differentiate something infinitely often, we can generate a power series from scratch using this formula. So we're going to actually use that formula to generate some power series. I think I put a couple examples. Oh, I also wanted to do for cosine, and I think also for sine. It turns out these guys have power series that actually work. Work in the sense that the function is equal exactly to the series. They're one and the same. But that will be a discussion for next time. So I'll let you guys go at this point. I'll give Maximus 3 points on test 1, and we'll stop there. So that's it for tonight. Have a good night, and I'll see you guys in the next one. Ciao.